Go ahead.
Okay. Hi everyone, we are the Thermoelectric team. I'm Justin.
I'm Jace.
And I'm Sebastian.
And the goal of our project is to explore the feasibility of using thermoelectric devices for low power wearable devices.
And our team name's WATCH, which stands for Wear Thermoelectric Carrier Harvester.
So a little bit of background information. Waste heat is basically heat that's produced as a byproduct of any process, and generally we see this as losses in a system. And waste heat, you see a big example in industrial and like exhaust gases. So normally that's energy that would be going to waste. So one way to recover these is through thermoelectrics, which basically takes a temperature gradient and directly converts it into electricity. So the human body also creates waste heat just as a byproduct of our bodily functions. We emit power at a rate of around 91 watts, which is about the same as an incandescent light bulb. So with a surface area of 1.7 meters squared, that gives us a heat flux of 5.7 milliwatts per centimeter squared. So in an area but the size of our wrist, that's about 57 milliwatts of usable energy.
So the picture over here, it shows a prototype we have done previously, and the prototype actually works on a hot place with like 37 degrees Celsius on the hot side. It also works with like hot gas steam, and it has been proven to work with our human body temperature for a transient time period of 12 seconds. So the goal of our project is to harvest body heat through engineering concept of like thermoelectrics. And our objective is to explore the energy conversion process through thermoelectric generators on like converting low-grade body heat into direct into electrical energies for a digital watch. And we also investigate the performance of commercial TEGs through analytical modeling, numerical simulations, and experimental testing. And we also apply engineering concepts such as heat transfer to optimize our system design. And here's a schematic showing like how to convert thermal energy directly to electrical energy, and using some voltage conversion devices, and eventually use those power to power our digital watch. And here's our organization chart. And because of there are some member changes, we actually merged our system into like 4 of our system into 2 benches. One is doing prototyping, basically creating the CAD design and identify what manufacturing material we're going to use, how to apply those fixtures. And as the models comes out, we will have the simulations team to run it and then test how additional components might affect the overall heat transfer, and that might change our cold side temperature. And the other team is working on experimentals, which we evaluate, like measure the performance, the currents, voltage, etc. A detailed more schematic will be explained later. And here's our enrollment, and we usually have like weekly meetings and bi-weekly meeting with our advisor. And we also share our documents through like Google Drive, and we communication using Slack, etc. And here's our timelines as we were in right now. We are in February 2019, and we have achieved 5 milestones already. But now we are working on like having the experimental successfully setups. We are kind of having some issues on that because our purchase was sent out like about 2 weeks ago, but we haven't received some of the component yet. But most likely we are working on how to modify the CAD and then continue like using a recursive process to analyze how the temperature gradient will look like. And here's our experimental setups, which involves heat sinks, some reference later for better integration with like thermoelectric couple. Because we usually thermoelectric couple, they have a wire that might introduce a separation on the surface. That's why we haven't been like review a lot of literature, and we try to like come up with ways to measure the currents, voltage, and temperature accurately. And we also decided to have like 2 subsystems. One is like in a stationary laboratory space, but the other part is portable. So we decided to have another portable system because we intended to like do measurements at different ambient conditions. For example, in the night times, the ambient temperature is much cooler, and the effect of like radiation can be like minimized. So that's why we decided to come up with another portable design that we can test it in like different conditions. And yeah, we expect the component to be arrived by next week and having set up.
So the main design requirement for our project is ensuring that we have enough power produced from a thermoelectric module under conditions of the hot side being your skin temperature and the cold side being ambient. So as a sort of back of the envelope, a digital watch that uses a 3-volt battery that has a capacity of 90 milliamp hours and a 7-year battery life. We see that to power a small digital watch, a minimum of 4.4 microwatts must be supplied. And this can be achieved through a TEG module of size 40 by 40 with 398 thermoelectric elements. Most TEG modules are constructed of bismuth telluride, which has a Seebeck coefficient of 180 microvolts per centimeter. And with a 5-degree temperature gradient, you could see that we have a 0.36 volts. So we would need to use a voltage boosting circuit. So that chart is from a manufacturer of a voltage boosting circuit, and we see that with that input, we can get about 2.65 milliwatts out of that. And then here's a couple more specifications that we have. The two most important ones are temperature gradient, and optimizing that has to do with our heat sink design as well as the design of our housing to ensure that heat doesn't get trapped or that it can dissipate. And then if we can't optimize that enough, then we might have to use multiple modules. And then size isn't really much of an issue just because we're using off-the-shelf 40 by 40 modules, so we can't really minimize that too much. And then here's a small prototype of the enclosure. It's going to be 3D printed. I haven't decided the material. I need to do more research on whether or not to use like ABS or PLA. But we want it to be, essentially it sandwiches the heat sink and thermoelectric assembly between a cage and a sort of top lid, and it's going to be held together by 3D printed pegs, and basically it works kind of like a pin lock. So the pin slides in and then you turn it 90 degrees, so the fastening is non-permanent, but we want it to be in case we need to replace any components. And then this is sort of like, I attempted to show how the grooves line up for when the pin moves in and then turns. And then also I need to research like tolerancing also, because for the SolidWorks model, it's like everything is the same diameter, but when we print it, it won't. So we need to find the tolerances too.
Yeah, so we ran a basic simulation for the temperature gradient of the first iteration that Justin just mentioned. And for our boundary condition, we set the hot side or the skin temperature to 37 degrees, and we assumed that ambient temperature was about 23 degrees. And so from that, we also set a natural convection to 10 watts per meter squared centimeters. And from that, we found that it gave us a temperature gradient of approximately 7 degrees Celsius.
So in terms of innovations, we are currently seeking into a new form of like thermoelectric generator. It's flexible and it's made of like polymer and some substrates as a substrate, and then having all those like copper interconnect laying out. And this actually has been like developed in a small scale and haven't be like commercially available. But we are currently reaching out to one of the company in Korea who replicate this. And we intend to have a combination of the rigid commercial thermoelectric generator and combination with the flexible one. So in that case, like, because the flexible TG usually they are great for like heat source with arbitrary strips, and this all improve like skin contact and minimize the contact losses. And here's the general data from the company we obtained, and they usually would give us about like 18.5 milliwatts and a temperature difference of like 90 degrees Celsius. And also they have a lower power density compared to the commercial TG, the rigid.
Yeah, so for the bigger picture of thermoelectrics, as of right now, thermoelectrics has a Carnot efficiency of about 6 to 10%. but in the future we're expecting like the material science research to increase this efficiency to about 10 to 15%. But for now we're starting with the application of a watch just as a first step with thermoelectrics, but there's also many other applications that we can really apply thermoelectrics to. For example, we can apply it to potential applications like low power microsensors or hearing aids using the skin temperature from your ear, or implementing a phone charger with your backpack using the skin temperature of your back. And yeah, so here's a breakdown of our budget. For experimental and manufacturing, it was cut about pretty evenly in half. Manufacturing consisted of about 55% of our budget, and then for experimental it was about 45%. Our total spending, we only spent $400, and we got $800 from Europe, and then we had additional fees or additional money from the amount of people that we had in our 189 project. So the total budget that we had was approximately $2,000.
That's the end of it.